Picture a massive scrapyard crane lifting tons of heavy metal, the doorbell ringing at your front door, and the glowing red coils of your toaster in the morning. What do they have in common? At first glance, absolutely nothing, right? But they all secretly rely on the exact same hidden force to work. Any guesses? Welcome to This Explainer. The answer is electricity, but we're not just talking about plugging your phone charger into the wall. We're diving into electricity's two invisible superpowers, magnetism and heat. If you're an 8th grader studying for your science exams, you are in exactly the right place. We're going to break down these concepts so clearly they'll be locked in your brain for good. Here is our roadmap for today. We'll start with an accidental discovery, meet the electromagnet, see magnets in the real world, check out the heating effect, look at fuses as circuit protectors, and finish up with electricity's hidden powers.
All right, part 1, an accidental discovery.
So, let's rewind to the year 1820. Back then, scientists literally thought electricity and magnetism were completely separate things, no connection whatsoever. But this Danish physics professor, Hans Christian Ørsted, kind of changed the world by accident. He was doing a classroom demo, just switching an electrical circuit on and off, and he noticed a compass nearby was twitching. He dug into it carefully and realized, and this is a direct quote, that electric current indeed produced a magnetic field. His setup was actually incredibly simple. You just take a basic battery, hook it up to a wire, and set a compass right next to it. The second you flip that switch and current flows, the wire suddenly acts like a magnet. The invisible magnetic field literally pushes the compass needle away from its normal north-south position. Turn the power off, bam, the needle snaps right back. That tiny little twitch proved that electricity and magnetism are a package deal. Moving on to part 2, meet the electromagnet. So, scientists saw Ørsted's discovery and thought, okay, how can we crank this up and make it stronger? Their answer was the electromagnet. If you're taking notes for your exam, you definitely want to get this definition down. An electromagnet is a temporary magnet made by passing an electric current through a coil of wire, usually wrapped around an iron core. The absolute key word here is temporary. It only acts as a magnet when the juice is flowing. And the coolest part is, you can build one of these right at your desk. Seriously, just grab a regular iron nail, wrap some insulated copper wire around it real tight, and hook the ends to a battery. The moment that current hits, your boring old nails suddenly gets the superpower to snatch up metal paper clips. It's like magic, but, science. Okay, listen up because this is a classic exam question they love to ask. How do you make an electromagnet stronger? You've got 3 main tricks. First, bump up the electric current. Just add more cells to your battery. Second, increase the number of turns in your coil. Wrap it tighter, add more loops. And third, stick a soft iron core right in the middle, just like the nail we just talked about. Lock those 3 things in your memory for sure. Quick question for you. Think about a regular fridge magnet. It has a north and south pole, right? Do you think an electromagnet has them too? Well, it absolutely does. But here is where it gets crazy. You can actually swap those poles just by changing the direction of the current. If you flip your battery around, north magically becomes south and south becomes north. You definitely can't do that with a regular magnet. Which brings us to part 3, magnets in the real world. How do we actually use this temporary magnetism outside the lab? Let's look at the electric doorbell. You've probably used one 1,000 times. It looks complex inside, but it's really just a 4-step dance. Step 1, you push the button, turning the switch on and completing the circuit. Step 2, the wire coil inside instantly becomes an electromagnet and violently yanks a metal strip called an armature towards it. Step 3, that strip has a tiny hammer on it, which gets dragged along and whacks the metal gong. Ding! But here's the genius part. Step 4. When that strip moves, it actually breaks the electrical circuit. The electromagnet instantly dies, releasing the strip, which springs back. This reconnects the circuit, and the whole thing repeats insanely fast. That's what makes the continuous ringing sound. All right, shifting gears to part 4, the heating effect. So what exactly happens when electricity faces resistance? Well, imagine you're trying to sprint through waist-deep water in a swimming pool. It's exhausting, right? You struggle, you slow down, you start sweating and generating body heat. Moving electrical charges do the exact same thing. When they struggle to push through a wire because of electrical resistance, a huge chunk of their energy gets converted straight into heat. Now, sometimes we want this heat, and sometimes it's literally our worst enemy. For desired heat, like in your electric kettle, an iron, or your toaster, we intentionally use a high-resistance wire made of an alloy called nichrome. We want the electricity to struggle and get insanely hot so you can make your morning tea.
But for unwanted heat, like the wires hidden inside your house's walls, we use a low-resistance wire like copper. We want the current to cruise through easily, keeping the wires totally cool so your house doesn't catch on fire.
And speaking of preventing house fires, let's look at part 5, fuses, the circuit protectors. A fuse is basically the ultimate bodyguard for your electronics. It's a tiny little wire built to intentionally self-destruct, just to keep you safe. To do this, a fuse wire needs 2 very specific superpowers. First, a low melting point. It needs to melt super fast, right around 200 degrees Celsius. Second, high resistance, so it heats up in a flash the moment too much current tries to push through. That's exactly why we don't just use plain copper for fuses. We use a special tin-lead alloy because it perfectly combines both of those exact properties. Here is how this tiny bodyguard actually takes a bullet for your TV during an emergency. Step 1. Normal current is flowing perfectly fine, everything's great. Step 2. Suddenly there's a short circuit or a surge and a massive current spike hits. Step 3. Because of that high resistance we talked about, the tin-lead fuse wire heats up insanely fast. Step 4. In a fraction of a millisecond, the wire literally melts and snaps, breaking the circuit instantly. Your fuse just sacrificed its own life, permanently cutting the power, but it totally saved your expensive laptop from exploding. Finally, let's wrap up with part 6, electricity's hidden powers. Let's zoom way, way out from that tiny blown fuse in your wall to the biggest example of this superpower on the planet. I mean that literally. We are living on top of a giant electromagnet. Deep, deep down in the Earth's outer core, oceans of liquid iron are constantly moving around. That movement creates massive electric currents. And like we learned from our guy Orsted earlier, where there's an electric current, there is a magnetic field. Our entire planet generates this massive invisible magnetic shield that blocks harmful space radiation. Without it, life on Earth just wouldn't be possible. So as we close out this explainer, I want you to literally look around the room you're in right now. Where are these 2 invisible superpowers hiding? Maybe the heating effect is glowing in the bulb of your desk lamp, or the magnetic effect is spinning the motor up in your ceiling fan. Electricity is so much more than just the thing that charges your phone. It's a total master of disguise, constantly transforming into heat and magnetism all around us. Keep your eyes peeled for these effects, really nail down how they work, and you are going to absolutely crush those science exams.